Hey, John here. Let's take a look at how you would implement a finite state machine using Verilog. A big thanks to everyone supporting my channel by subscribing, liking videos, even just watching the darn things. Get those view counts up, as well as my Patreons, especially the VIPs over there. Thank you very much. Well, I added a new directory to my Verilog examples repo over here on Github called FSM. And inside here we got a couple of examples here, 5 different examples. The first 2 I just want to throw together the basic structure of a finite state machine. And then these last 3 are actual implementations of the example state machines that I put in this handout here that I go through in some level of detail in another video. If you haven't already seen it, or you don't really know what a Moore versus Mealy state machine is and what the difference, why they exist, click on the link in the description below this video on YouTube to go find the playlist and back up and have a look-see in there. I'll also include in the description below this video a link to a university faculty page where I used to post all these handouts and stuff like that, so you too can find the PDF that I'm going over here for the examples. So this is where I've cloned my examples to. I'm in the FSM sum directory, and here are the various examples. So the first one, here's my reminder to myself. What's so unique about this one? We have a Moore-based finite state machine that uses a single always block, which is not recommended for general use. But I want to just get the basics done here, and then we'll build up from this to build more interesting and sophisticated ones, and we'll see why why the single always block style is not recommended for anything serious. Okay, what are we going to do here? The single always block in this example will calculate the value that represents the next state of our system, and these are expressed using a simple binary number where state 1, state 2, state 3, and so on are just stored in a multi-bit binary value called state or S or something like that. Okay. The other thing the single always block has to do is wait for a clock edge to come along. This one's going to use the rising edge. Every time there's a rising edge of a clock, it may change the state to some other state, and it depends on the design. I think this is a free running counter with a reset, so the state will change on every clock edge. It'll either be reset and go back to 0, or it'll count by adding 1 to the current state value and storing that back in our state register. We have a top level test bench here and a single module that holds our state machine implementation here. So what do we got here? We've got the module. We have a parameterized module, just to show you an example of how do I use one once in a while. This will be the number of bits that are in our counter that we're instantiating here, or defining, I should say. We've got an input to this module, which is the free running clock, which every time it ticks will advance, unless we reset with this guy here, which will 0 our counter on the next clock. And we have a state register called D, in which we store the current count with the appropriate number of bits based on the value of the width parameter. So what do? We have a pause edge on clock, and we simply say if the reset is being asserted when we see the pause edge, we reset the clock to 0, the counter to 0, I should say. Otherwise, we add 1 to the current value of the counter and store that in the counter register. Now let's think about this for a minute. What we've got here is a flip-flop, an edge-triggered flip-flop, and it's got a synchronous reset. This is a standard model for a D flip-flop with synchronous reset. We saw this earlier, okay? Now, if you go read the Clifford's notes that I refer to in my series every now and then, he would prefer that you do this, I mean, cosmetically, and he is not completely without merit here. One of the arguments he makes, which is the most valid of all, in my opinion, is that if you don't put begin and end in here, this will, of course, still work because if and else is a single statement. Remember, you only use begin and end if you have more than one statement in here. Well, if you have a synchronous flip-flop, any flip-flop really, and all you're trying to do is update it on its, sensitive edge, and all you're going to do is reset it or, store a new value like a state machine would have it. You don't want more than one statement, and by eliminating the begin and the end, you can't put more statements in here and do something stupid like throw some code up here before this if or after the else. It becomes a syntax error. So, okay, fine. If you want to take an extreme example on this incredibly simplistic case, okay? Just saying. You'll see both opinions, I guess. Pick a style and stick to it. I think it's more important to stick to a consistent style than it is to, to change your mind every time you open a new file. That would really be annoying. Anyway, so what do we got in here? We've got D+1. This is a combinational circuit that exists. It will be continuously calculating the value of D+1 at all times, no matter what. And only when there's a pause edge on the clock will it, if not reset, it will then clock it into the D latch. Okay? Let's take a look at our test bench. Couple things in here. First of all, I decided to override the parameter, give you an example on how that all works. There's a POW function in here that's that I use to demonstrate one way to use this. When you got a powers of 2 and you want to have a single variable, I want a 4-bit, I want an 8-bit, I want a 9-bit, whatever. If I change this number here, this function changes there, and the max value then also gets updated, okay? So counter max is used to represent the total number of count values in our instantiated counter object down here. It's not the maximum value. This is probably not a good name for that, but we'll leave that some other time. Counter max represents one more than the maximum value you will ever see in the count coming out of our instantiated counter down here, okay? Now I was playing around with this. Let's put this back on 0. This is what's in the repo right now. That's why I have a little comment here. Let's come back to this a little bit later. We're going to start with 0. We're not resetting. We have a count bus here that we're going to connect to the output of our FSM. We need a place for it to go. It has to have the right number of bits. So if I change this, this will change. The number of bits in my counter instantiation will change, and everything will be all synchronized together. I don't want to use the word synchronized, but configured and correlated so that everything fits and is correct at all times. We connect the clock, the reset going into our module. The D value in the module comes out on our count bus. We have a free running clock. Every time we move one simulated time tick, we flip the clock over. Now that means up here, what I got is 1 nano over 100 pico. That means that 1 here represents 1 of whatever I set up there. So that's 1 nano. That's a gigahertz. Unrealistically fast clock, but it's fine. Don't worry about it. In simulation, we just need to have some time base, all right? The 100 pico over here means that when it outputs its waveform into the VCD file, how many digits and what does each digit represent? What's the resolution or the precision, as they say? I talked about all this before. The reason I do this is so that we can do fractional increments on our time if we want to, just for fun. And we'll look at that in a minute because there's some issues in here that you need to be very aware of when it comes to creating your test benches. I probably should have talked about this long ago, but let's just get rid of it right now because it may or may not affect this when you're running your simulations, okay? So what else do we got going on here? A single initial begin dealy here where we just run through and diddle and daddle with the various values and then finish down below, okay? What are we going to do here? We're going to monitor the reset the count value. Why not? I'm going to dump out the values that I calculate to make sure I did that right. We're going to dump stuff to a file. We'll come back to this in a minute. We're going to waste a little bit of time to let the clock tick for a while. Then we will assert reset. Remember, we started with it 0. Then we will turn reset off after 4 ticks, which, remember, that's two entire cycles of our simulated clock up here, because it takes 2 of these before it, 2 high and 2 low before it completes one full 360-degree cycle. We wait counter max times 2 plus a little bit extra so that the counter has a time to go through its full range and wrap around. That's why I needed to know counter max. Then we will assert reset for 1 full period of the clock and turn it back off and let it count some more. This checks our ability for our module to reset itself with 1 single cycle of the clock, which is critically important to make sure I did that right, okay? So this tests enough of our module that things can be interesting. We can get something interesting out of it. Now, looking at it in here is fine and dandy, but this is going to be easier to look at using a waveform diagram. But you can see the thing being reset in here. You can see it counting. You can see that each one of these is going up by, what? 10, counting by tens, or in this case, tens. It goes from 0 to 100, then 110, 40, 50, 70. Well, we're counting, whatever. We're counting by whatever. During the reset and so on, remember I had like 10 cycles, and I had 4 or 8 or whatever. So as we do all this stuff, we're making these leaps forward. All right, let's go ahead and do a make plot. I didn't look that closely at the display output anyway, because when you're doing something like this, I invariably look at it this way. Let's look at all these values, and then open this up, go into our unit under test. Now, all this stuff is connected to the output anyway, so I guess we don't have to care about any other things. If you hit this little bugger right there, it scales it to fit on the screen, and it does what we hope makes sense at this point. All right, let's zoom in a little more on the left here. What do we got? If you highlight one of these things, I don't know if I showed you this before. If you come up here, you hit show wave highlight. That's under the view menu up here. See this big blue bar over here? If you click one of these, the bar runs across the screen. It's very useful when you got a bunch of stuff on here and you want to say, oh, which one is the thing way over here? At least you know that's the count, okay? You click reset, it lights the bar up. Okay, so maybe that will help in certain cases. Turn it, well, that's not what I wanted to do. I wanted to rescale it because I moved this over. For whatever reason, this particular version of the GTK Wave always hides these values. It drives me nuts. Hopefully by now there's a newer version. Anyway, what do we got going on here? Okay, now inside our unit under test, remember our always block had a pause edge to update the flip-flop. So if we look at this, there's a negative edge. Here's a positive edge. That makes perfect sense. Resets asserted when there's a positive edge on the clock going in the unit under test. That is when we reset our latch, and we see that coming out the count output of our module and from the perspective of the test bench when I added these signals. All right. The reset goes off here. It's also on a falling edge. I purposely set this up so that the reset changes at a point in time that is not the same as the edge of the flip-flop inside the unit under test. Because if you don't do this, it's going to get annoying. Okay? Your setup and hold times are violated. It's plain and simple. We'll look at that in a minute. That's what those comments were that I said we'll come back to. Let's look at the normal case when it's working correctly first, okay? So reset goes on in no uncertain terms at a point in time where it won't make any difference. We reset it synchronously. It stays on. It gets reset when it's already reset. It doesn't matter. That's okay. It goes off when no one's looking. We have a positive edge on our clock, and we see the register being updated with D plus 1 because D was the value 0. Now it's 1, 2, 3, 4, 5. And we see it counting up. I scroll to the right here. Once we get all the way up to all ones, which in hex is F, because I made a 4-bit counter, remember? We clock it again, and it'll just go back to 0, 1, 2, 3, 4, 5, and so on. When we get up to 3 here, because remember it did the total number times 2 plus 4. So that's 1, 2, 3, 4, 5, 6, 7. I don't know, what did I do? Did I do total count plus whatever? I waited long enough so that we wrapped all the way around. Then I asserted reset for one full cycle. There you see the reset. Reset goes away. The next clock, it goes back to 1, and it keeps on going. All right? Let's get this out of the way. I was a little confused there for a minute. What's going on with our time down here? What are you? Counter max times 2 plus 6. So that should have been 3 full cycles after the reset came off. Plus the counter max was 16 times 2 is 32. It should have been 38 total ticks, right? And this is a waste of time. I shouldn't be doing this right now, but just for my sanity's sake, what's going on there? Did I count wrong? Well, 36, or rather 38, should go full around once plus 2, 4, 6. But it started over here. So the delays that we're talking about start here. They don't start there. It starts here. So that means it had enough time to go all the way around to there. That would have been the point in time when I had count times 2 plus, if you highlight one of these rows and you put the cursor on here and you use your left and right buttons, it goes to the next edge. So it'll be real easy to count these. 1, 2, 3, 4, 5, 6. There's our 6 edges. I have confirmed the world makes sense to me. If it doesn't make sense to you, you need the Zenith Colortrak System. Okay, let's go back to the top here. Let's look at these notes. What happens if the setup and hold time if we start clock with a 1 instead of a 0? Well, let's run it and find out. Make plot. This will be more reasonable. There we go. Grab the plot. So what we've done here is shifted the clock by 180 degrees. If we do this, look what happens. Let's zoom in right here. What we're doing is we're changing reset in simulation time, the same time, at the same point that clock flips in the edge that the unit under test, our flip-flop in the counter, is sensitive to. And we used blocking assignments. We used blocking assignments when we flipped the clock. We used blocking assignments in the initial part of the test bench when we're changing the value of clock. We pound whatever. This was like 10, I think. And then there's a reset equals 1, and then a pound 4 or something, a reset equals 0, and so on. So the question then becomes, did reset go high before the clock went up, or did reset go high after the clock went up? And regardless of the order of those, in what order does the simulation of the flip-flop run? We got 3 different always blocks, or we have 2 always and 1 initial. In what order do those 3 things start? Well, it turns out that the always block in the unit under test, which is our flip-flop, is triggered after and by the fact that the clock went into positive edge. So we know for a fact that the always block in our module will run after this rising edge because, like I said, that's what causes it to go. So that helps. But did reset go up before or after that other always block gets scheduled? I don't know, right? Well, it turns out you can tell by looking at this that clearly that always module And the unit under test must have run after the reset was high because it saw that the reset was high on this leading edge with 0 setup time. Okay? So this is a really crappy test bench. You could probably run it a dozen times or maybe upgrade Yosemite, or this is actually Icarus that's doing the simulation here. It might not react the same way. This is a real dumb test case, okay? Don't do this. It is ass. If you look up ass in the dictionary, you'll see a picture of this waveform. I'm just saying, okay? Now, let's say you're in a situation where you kind of have like no option due to the complexities of a realistic design. You got billions of lines of code because, you know, that's what our hobbies are all about. And you do want to move it really close to this point in time. Well, there's various ways to do that, including something along the lines of this. And that is why we have 1 nano up here over 100 pico. This is 200 picoseconds of delay. So now what I've done, by putting this in here, and it's much more obvious if you make plot, I have just simply skewed back in time all the subsequent updates to all of what's going on in that initial block that I used to rise the reset, to lower it, and down here like this. So if we zoom in now, we're back to, again, being clear in no uncertain terms what happened, in what order. So I'm no longer violating the setup and hold time. If I did this in a real circuit, that would be tough to, to make sure you got right in a real circuit. And also in simulation, even to the human eye, this is clearly not ambiguous if I do that, okay? So when you create your test benches, what I like to do is move these signals around 180 degrees out of phase with the time in which the main system clock is triggering all my always blocks that are updating things like counters and state machines. Okay, so that's what those notes mean. Let's move on. If you don't get it, just tinker around with it, plot a bunch of stuff, change the values, see what happens. Your mileage may vary. Here's the second example. What do we got here? It's got 2 always blocks instead of 1. It's going to do the exact same thing, except rather than ramming everything in 1 always block, we're going to have 2. The test bench is the same in both cases, although, remember, I just hacked the one that we were just looking at, because this one has it starting at 0, and this is still commented out. In fact, you could argue this is not exactly the same, because the other one had a 2, and this one had a... You know what I'm talking about, okay? So, otherwise, they're identical to the first test run that we saw. Let's look at what's happening in here. What does it mean to have 1 always block versus 2? What we've got here is simply I've removed the D non-block assigned to D+1 out of here. Get it out of there. Put it down here. Factor it out. Okay, what do we need to do in order to make that happen? We need to find a register within which I can write something into in this other always block down here, so that it exists in some way, so that when this thing triggers and our flip-flop wants to update the state that it stores in the D reg, it has a variable that it can copy in there, okay? Now, in a realistic state machine, what happens is this is sufficiently complex where you can't just throw this massive monstrosity of yick barf in this guy here. Can you? Yes, you could. If you really wanted. A lot of people do that. Feel free to Google around the internet. A lot of messy crap that people do in their code. Just don't do it that way. If you have a really strong opinion against 2 always blocks or 3, I'll show you a 3 always block a little bit later. In your style, let us know in the comments below. Justify your opinion. I much prefer to factor this stuff out. And I've seen enough people suggest this and give reasons and rationale that, I mean, you could probably dedicate an hour or 2 of discussion, the pros and cons. In fact, in those clip notes, and if you don't know what I'm talking about, my links here, I'll show you how you can find them. There's my NIU faculty page. If you go to the Verilog examples here, I've showed you this more than once. If you're just joining the series in progress, documentation notes, blah, 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 Verilog notes. The Cliff guy is this guy here, okay? See these Cliff notes? Here's a couple of them. Maybe I'll add some more links. But in reality, what you want to do is go over to this site. He must work at or represent Sunburst Design. There's a whole bunch of papers down in here. This guy has all kinds of dialogues about why you want to not ram everything into one always block. He's got a lot of opinions on things like why you have begin and end around your always blocks. He's the guy that doesn't like this, and so on. And you can read all these opinions, and it will gain you more insights into what Verilog is all about and help you develop a style that works best for you, that you think is, useful and productive when you're sharing it with other people. And that's why I like to make sure that you have exposure to not just my opinions, but everybody else as well, that at least I'm aware of, that have good, solid justifications for why they suggest what you should do. All right, so that's what's going on here. Combinational circuit. This is purely combinational. This is the sequential piece of our state machine. And if you go back and look in here, and this is a Moore style state machine, because in a Moore style state machine, the output here is purely based on the current value in the latch that holds the state of our machine. Turns out there is no combinational circuitry at all here in a counter, because there's nothing to do. The count itself is, in fact, the value that comes out of the state machine. So this circuit is a buffer or a non-existent thing. You know what I mean? The arrow just comes straight out. The key here is this, that there's no input over here, like the reset signal in this case, does not have any direct impact on the output over here. The only thing coming out of this is based on the value that's stored in the sequential latch. That's what makes it more. Okay? The state machine diagram right here matches the implementation we're just looking at. If you haven't looked at the video, the short of it is, in a Moore style state machine, the state itself represents the output value without any respect to the current inputs. The output, therefore, can be specified inside these bubbles like this. There's the current state is 0, the output is 0. In a counter, that's what you get. If the enable is a 1, you go to the next state and you update the value to a 1. The output then becomes a 1, and so on. If the enable bit is a 0, that's what this thing actually is based on. I probably should have modeled this instead of the one with the reset. We'll see this one in the next example now that I think about it. This is the next example. I have the enable and the reset, so this is still worth doing. It's a foreshadow instead of a summary of what we just saw. I apologize for that. Point is that each of these bubbles in here represents the current state, and in a Moore style state machine, the bubble itself represents what the value of the output will be, and we list both the current value of the state, however we identify it. In this case, it's a number, and we put in there also the current output value as like a denominator of a fraction type of thing. The inputs are on these arcs that go around like this. In this particular case, the input represents the enable. It says, yes, you can proceed, or no, you cannot. If the enable's off, every time the clock ticks, we simply stay here. If the enable's on, the clock ticks, we move to the next state and go around here. If that's not enough of a review of how to read one of these, go look at the previous video where I walk through this in agonizing and painful detail. That video at this point is about 4 years old. I just reviewed it recently, and I'm not really proud of it. Probably was a first take. Maybe I should update it at some point. Throw in your comments if you think it stinks or not. Let me know before I record it so I can address whatever other issues, other than the obvious ones, I'll leave to the laughter of the viewer. Okay? That's a Moore style state machine. Okay, the combinational circuit down here is the thing, my point, that's in this box over here. We do not have one over here in the particular example we're looking at right now. We will in a minute. Okay, so now back to here. Let's go back up and around the horn to FSM2, which I think is more akin to what we were just looking at. I know I put one of these. Here we go. A single always blocked Moore style FSM. Calculate the next state, flip-flop, blah, 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 same sort of stuff. Okay, what do we got? What do we got? FSM. 2-bit synchronous counter with enable. It also has a synchronized reset. So what do we change? We got a clock, we got a reset. We have the current state stored in a 2-bit value. I do not have a parameter in this one, so it's just hard-coded. Keep it simple. No extra examples this time. We have an enable input as well. So what this is going to do is when enable is high, we're going to proceed to the next step, next state. It's this arrow here, the edges between these arcs here. The 1 is enable, 0 is disabled, you could say. All right, so that's what E is. S is simply the current state or the count. In this style, what we've got are 2 registers. You could say we had that before as well. And when we looked at last time, remember that the output was a reg. The D value was a reg up here. This style here is in keeping more with what Pong Shu does in his examples. We go back here again and look at the Verilog notes. In here, there's a guy named Pong Shu. If you look at these books, his style in this situation, I'm remembering when I read his book, he said he never likes to see regs up here, only wires. You put regs down here, and this is even his naming convention for the next and the current state. Okay, S reg represents a real flip-flop. S next represents a reg variable type that will be the next state you'll see down here in a state machine. And S next will be the output of our big combinational circuit down here. So that's his convention that I adopted early on. Was when I read Pong Shu's book, was the first time I actually felt like I could understand anything at all about Verilog. So I give him high regard, deserving or otherwise, simply because it was after reading his book that I could actually write something that worked. Okay, so I know his advice works. It may not be the best, but I'm certainly not going to shoot it down. Between him and Cliff Cummings, these 2 guys, I'm pretty confident they know what they're talking about. And every time I look at anything, I'm like, yeah, they're pretty much right. And the Cliff Notes papers win awards at conferences and things, so it's just not me and him either. That's a lot of people getting together saying, you know, this advice probably doesn't suck too bad. So I'm just saying. That's why I have those links in there. So what do we got? We have to know the current state. We're going to have a place to put our calculation that represents the next state. And what do we got here? Advanced FSM, the rising edge clock. The reset logic is here to ensure that synthesis recognizes the always block is, in fact, a flip-flop with a synchronous reset. And I wanted to make sure I punch this point, because if we look at this, okay, foreshadowing. We've seen this before, and remember I had a video where I talked about how there was recommended, let's call them design patterns. That's a phrase from 20 years ago that people kind of bought into, how you write code, what styles, what do the individual chunks of code look like that accomplish specific kinds of functions, all right? So in that context, this is the design pattern for a flip-flop that has a synchronous reset. And this is actually a spec that comes from, the IEEE Verilog committee. They say if you want to model a flip-flop that has a synchronous reset, put a single edge clock in here with nothing else, use the reset signal here, assign it a constant value, either a 0 or 1, in order to reset your flip-flop like this. Have an else statement with nothing else in here, without any other sensitivity things in nothing else listed, I should say, in the sensitivity list. This will then allow the synthesis tool to infer that this really is an edge-triggered flip-flop, and that the clock will update the data output based on the assignment that's in the else statement. And by the way, I always use non-blocking assignments, okay? Now, that's how you want to update your state register for your state machine. I say this and punch it because if you go back and look at some of my earlier videos, I have what is a state machine, and I have some extra if-then-else's down in here that, let's come back to this, all right? I don't want to get through this before we get enough to get the basics. Short of it is, this is the proper design pattern for a synchronous reset on a edge trigger flip-flop. We'll come back to let's put a pin in that and we'll come back to it. So what are we doing here? This is the combo block to update the current state using the inputs, determine the next state. What do we got? I discrete binary because, yes, this is trivial. You could easily just put S next equals X reg plus 1 in here. Or maybe if enable is true, set s next equal to sreg plus 1, else set s next equal to sreg if I wanted to, and collapse this whole thing down. All right? That's what this is in reference to, like this over here, okay? Now, the reason I did this explicitly and burned up all this visual space, all these electrons going on, or photons, I should say, burning up the screen here, is because normally we're not just counting something stupid simple. Very often we're doing some more complicated things, and you end up expressing it more like this. So we're evolving this simple case, while the case stays so simple that it's ludicrous to do it this way, just so you understand this framework. It's another design pattern kind of thing, okay? So follow along with me here. What are we doing? Combo circuit. S next equals garbage. I don't care, okay? You do this. It helps with debugging. Why does it help with debugging? What if I screw this up and don't assign a value to S next because I leave one of these out? Or something else goes awry in my design. If that happens, S next will be left with garbage in it, and the simulation will turn it red. It'll be obvious that I screwed this up, okay? That's one of the reasons you do this, okay? Now, so by default, set it to XX. Then you say, based on the current state, keep in mind we're doing a more style state machine, and a more style state machine, the next state, which is this arrow here, the next value we want to put into our sequential latch is based on the current value and any inputs, okay? Now, we actually have two inputs, one of which is called E for enable. The other one's the reset. We'll come back to, that's the pin that I just left stuck in there. We'll get the reset back in a minute. The enable input is the only one that we're going to concern ourselves with in the combo block down here, okay? And if the current state is 0 and it is enabled, the next state should be a 1. Otherwise, if it's not enabled, the next state should be a 0. This matches our state diagram that we were looking at a minute ago, this thing right here. Current state is 0, input is 0, come back down here and stay in 0. Current state is 0 and the input is a 1, go over here. Okay? So this is a perfect match to the state diagram we're looking at. There'll be a case in here, or an entry in here, an item, I think is the word that the Verilog spec uses, for each one of our states. Which state am I in? What do my inputs look like? Determine the next state when that input is true. Determine the next state when it's false. And you can see here I go from 1 to 2, 2 to 3, 3 back to 0. If the enable is on. If the enable is off, I'm in 0, stay in 0, 1, stay in 1, 2, stay in 2, 3, stay in 3. Okay? There you go. Now, the other piece. Because I have a reg and a next, and this output is a wire here, I can't really just assign a value to that wire from inside an always block. I have to do it with a continuous assign or something else. Okay? So on the very bottom of this file, I want to make sure that the sreg, our current state, which represents the count, because I have no circuitry over here is the point. I need to get the current value of the state out of our state machine. Now, quite often, you will have a complex circuit over here, which is the foreshadowing in some subsequent example. In this case, the circuitry is trivial. Okay? It's non-existent. We simply go down here and we say the state value itself is the value I want to output from my module. Okay? So let's go ahead and make plot. Go ahead in here, open that bugger up. And what do we got here? Blah, blah, blah. And we see it counting. We're doing various resets. This is wonderfully complicated. We're going to have to go look at the test bench and come back to this. So we got two things that we need to talk about here. One, my half-finished digression on this whole thing. This design pattern, as I said, is how you make a flip-flop with synchronous reset. Period. In order for synthesis to be certain, in order for me to be certain that my synthesis will generate a single flip-flop, that has a synchronous reset, I need to do this. It might be smart enough to do it in other ways, but this one, the spec says use that. And this is why. Down here in the combo circuit, I don't say if reset, set S next to 0, else do all this. I could do that, and it would work perfectly in simulation. You would not know the difference. If the simulation tools are worth their salt, it would have figured it out anyway and made this flip-flop be one that has a synchronous reset. And by that I mean, if you did say, if reset is true down here and said S next is 0, I mean, think about it. That's really what's going on here. S reg is S next. If you put S next, if you delete all these 3 lines here and just simply said S reg equals S next in this always block, it would definitely work in no different way than if you put these 3 lines right above this case statement down here. Okay? In simulation. But when you synthesize it, will the tool realize that your intention was to implement a single flip-flop that has a synchronous reset and not create a bunch more combinational circuitry? And that's the problem. It could burn up a lot of extra LUTs and stuff and create an inefficient design if you don't follow the rules. All right, so this is one of those things where logically it makes no difference whatsoever, but in reality, depending on the quality of your tools, it might matter. Or in fact, it will, because I put depending on the quality. Can always get a crappy quality and it won't work. Okay, moving on. Let's look at the test bench in here. What do we got? We got a clock, we got the reset, we got the enable. They're all low. We got an output wire bus coming out of our unit under test in the obvious way. Connect to the clock, reset, enable. State all goes in here and comes out. The state comes, all these 3s go in, the state comes out, the clock flips up and down every tick. What do we got on our time base? 1/100 pico. Monitor will not trigger on things changed in other modules. We saw this once before. It's a stale comment, really. It's not false, but I try to get rid of the stuff that's too stale so it doesn't clutter things up, like my digression here. We're dumping the usual stuff. What are we going to do? We're going to write 4 clocks, assert reset for 4 simulation periods. This is 2 clocks, right? And then we're going to turn it back off. We're going to enable it after a while. So we're going to assert reset. Then we're going to turn off the reset. Enable must start 0 up here. Correct. We let 2 full cycles of our clock run before we enable it. Then we let 6 whole cycles of the clock, right, run. And then we turn it off for 3 more full cycles. Then we reset it for a while. We enable it while it's reset. And then we turn the reset off while it's still enabled and click some more. If you think about it, these all check these separate cases where is it enabled and reset at the same time? Is it enabled when reset is deasserted? Is it disabled when reset is deasserted? So this checks a couple of different scenarios, right? And I would argue that the simplicity of the code suggests that we can just look at it and know it's okay. All right, this is not a complicated design. We shouldn't have to go to test it at this level, but I show you this because in a real design with sufficient complexity, it can get incredibly confusing, and you really do need to check all these different cases. Can it come out of reset if the enable is on already? Things like that, okay? Come on, light up my stuff here. Now we're just counting, so we don't really care about what's in the unit under test because this is all copied up to the outside anyway. Maybe we'll look at sreg and snext just for fun in a minute. That's probably useful at this time so everybody understands the get your mind around this, okay? So let's go ahead and turn on our wave highlight here so we can look and see what's going on. Clock free runs, enable. Goes on, it goes off, goes back on again. I was talking about the enable relationship to the reset, right? So we wait a couple of ticks at the beginning of our simulation, then we assert reset. It is not until we have our leading edge triggered flip-flop that updates the current state with a known value. Before, over here, we did not have the counter enabled, and our combinational always block assigned S next to double X. And when it came online, I'm sure that S was double X as well. In fact, that's what comes out of the state machine. So it boots up with double X. I never initialized it, right? And I never reset it, and I never enabled it. So really nothing can happen that the simulator can tell us with any, definitive results what could happen. We never updated or assigned a value to the state register in simulation, okay? It can't do it. So it's not until we got an active reset and a leading edge that we see the current state becomes 0. The reset continues on. It resets it again. Doesn't matter. It's already reset. You put 0 into something that's already 0. Nobody saw it. No one cares. Reset goes down, but we're not enabled. Let's come back up here and then scroll across like this. And we come in contact with a leading edge. Nothing's enabled, nothing's happening. Trailing, doesn't matter. Leading edge on the clock. What's going on? We're not enabled. Stay where we're at. Falling edge on the clock. And again, I synchronize or I adjust all my simulation waveforms so that they don't coincide and violate the setup and hold times. So that's just me changing the enable before the active edge of our clock says I better change my state to a 1 because I'm enabled. Okay? Come down, go back up. I'm still enabled. Count to 2. Come down, go back up. 3. And wrap around back to 0. Go back to 1. Go back to 2. And then we disable it and the clock is still on. And we see we stay in the current count because we're disabled. We then assert reset, and on the next active edge, we see it slam to 0, because that's what reset does. Here's where we enable the counter while reset is on at the same time, and we clearly see that reset takes precedence over the enable, and that's true because, background that, if you look closely in here, we're saying if it's reset, set sreg to 0. Else, say, put in there whatever the combo down here says to put in there. Because the combo down here always says put in, the current value plus 1. It never gets here when reset's active, which is why it stays 0. Okay? Combo circuit's always running anyway, but we're just going to ignore it because the flip-flop looks at the reset before it considers anything coming out of the combinational block. All right, we deassert reset while enable is still on. The next clock edge that comes along that we're sensitive to causes the clock to count up. Okay, so this is exactly what it should do. All is well. Let me find my window here. Okay, here we go. Now, let's do another make plot. As I alluded to moments ago. Let's have a look-see at all these signals. Plus, in here, let's look at S next. We can look at both of these if we want. It'll be the same thing as the state coming out. As you can see, state here is a copy of this because remember there's a continuous assignment that says the S output of the module equals sreg, and in the test bench at the top, that value is assigned to state. So these two signals, I drag them down here, are identical all the way across. So I'm going to simply delete this one. It's visual clutter. Okay. Turn on our big wave. All right, look what's going on between S next and the state. Actually, let's put this one below. Okay, so what do we got here? When enable is off, remember the Verilog for the combinational block said that S next shall equal state, and it does. Enable's low. S next equals state. 0 and 0, same thing. When enable goes high, S next down here all of a sudden is a 1. That's because it shall be equal to the current state plus 1. Without any regard to anybody else. This is the output of a combo circuit that says if you get a leading edge on the system clock and we are not in a reset, this is the next state that should appear in here. And it does. 1 goes to 1. Here's the 2. Why is there a 2 here? Because it's enabled. And the current state is 1. The combinational circuit is in there all getting ready to calculate what the next state should be if the enable is true. And we are not going to reset it. So when you got a 1 there, the combo will calculate 2. We got our leading edge on the clock, and it copies the next one into the current state, and the combo does its job and says, okay, I'm enabled, and I need to calculate the current state plus 1, which is 2 plus 1, which is 3. Leading edge, the 3 from the combo gets assigned to the latch. The current state is 3. We're still enabled. The next state must be 0, and so on, so on, so on, so on, until we get a reset. Now, keep in mind that the combinational circuit does not care about the reset. It only cares about the enable and the current state. We are disabled. It's low. Current state is 1, 0, which is 2. We're disabled. Therefore, the next state is the same as the current state, which is 1, 0. That's why these two are the same value here. Look what happens. On this leading edge here, when I have a 1 in there, I calculated 2. We got a leading edge that copies into the state. Current state's 2. I'm enabled here. Combo circuit says the next state better be a 3 because I'm enabled. Then it goes low. Wait a minute. I changed my mind. Not enabled anymore. The next state shall be 2. Here's our leading edge. It stays 2. It stays 2. It stays 2 because we're not enabled. That's why it stays the same. Okay? And when you look at both, the current state is my point, as well as here's the calculation of what the next state should become, provided that the enable line, in this particular case, the inputs to the circuit as a whole, don't change. That's what it would be if nothing else changes, and we run into our next active edge of the clock over here. But we don't. We have an input value that changes before we got there, therefore the next state value does change. And that's what gets assigned, or stays the same in this case, in the state variable. Okay, so down here, the same thing also holds. Reset goes active. And therefore, on the active edge here, the flip-flop will be reset without any regard at all to what the combo circuit says. The reset takes precedence, all right? That's because the flip-flop says if reset's true, set it to 0, I don't care. It doesn't even look at S next. Okay? Now, after that happens, it just so happens we're not enabled, and not enabled means that S next equals the current state. That's why 0, 0 is in here. Then we got an enable. Then we say the current state is 0. The next state shall be 1 if we got a leading edge, which we do. But reset is still on. So reset still takes precedence, reset finally goes off. Combo down here doesn't look at or concern itself with reset, which is why this stays 1 the whole time. When this reset goes down and enable is still true, now we got a leading edge when we don't have the reset on. And the next state gets copied up and so on, all right? So this is really useful to figure out what's going on when you screw up your designs. Okay? You really want to get that in your head, how to optimize, design your test benches so that you can always see what's happening on these waveforms. Now, look at the clock on the wall suggests to me that this video is going to run way over time if we continue looking at the third and fourth examples in here. These I will leave to next time. Foreshadowing the third and fourth examples are to move on to these message recognizers in here. Okay? Grab this handout, read through it, make sure you can make sense of what these state diagrams are. I'll record this one for next time, all right? It'll be the Mealy and more versions of this so-called recognizer. If you go to my old faculty page, what happens is, and there's a link to this in the description below this video on YouTube, what happens in here, this lecture here is me talking about that handout, okay, where I explain the recognizer and I walk through it. I recently viewed this video. I ain't proud. It probably needs to be updated, but I don't work there anymore. Maybe, like I said, throw some comments in there if you like it or hate it and what is great or bad. Maybe I'll re-record it for no other reason than to put it in this playlist at some point and freshen it up. I'm showing you this not because of that, but because of this down here. If I'm not covering the bases in a way that you understand it, there's a link here to someone else explaining Mealy and more, and he uses the exact same examples. When I sat down to record this, doesn't matter which example I used, I purposely went around the internet to find other videos and help and how-to pages and things like that, and I found this one. And I said, I'm not going to explain it the way this guy does. And that's my point. But I'll use the same example. That way, a student, if they don't like my style or I say something dumb or just outright wrong, they have a second shot at it down here. This can be a complicated topic for some people if you're not used to these. Your first exposure, this might be a big lift, okay? So you got two shots. Here's somebody using a style and technique and description. Here's my version and my handout right here, okay, that we were just looking at. Have a look-see at all three of these. We'll come back next week, and I'll take a look at these more complicated state machines using the style that I just showed you, the 2-always block state machine design in Verilog, and I'll throw a three always blocker in there as well. All right, so after that, we should be armed and dangerous to do just about anything we want with state machines. Thanks for watching. I'll see you next time.